Hello everybody and welcome to the third video of our course Deep Learning. And in this video, as I promised you in the last video, after we saw how our brain, not actually the whole thing, but what we need, our neurons, how do they interact to generate an output in our brains. Now we're going to see how we make an artificial uh, you can say brains that mimics our brains. And first we're going to start with artificial neurons, and then we're going to go to see some model for a set of neurons to construct some kind of like small artificial brain. And then we're going to see how the computations are done in this model. So first, the neural model. Uh, as we have in the real life or in the normal machine learning, we saw before, or before, we have an input. Imagine we have two inputs like x1 and x2. Then okay, x3 also. Then we going well, like you remember from last video, we saw the dendroids. So we're gonna feed these inputs through dendroids to a cell. So here we feed the dendroids to the cell. And as from before, we in machine learning we had like these things we called weights. So the the canal to feed to the cells are the weights. Of course, we have a bias too, so we're gonna feed also the bias to the cell like without any input, as we did before. Then the cell going to have output, and that output is actually our hypothesis function. So that's how we took the traditional machine learning and upgraded it to have like an actual neuron model. And as you know from our last course, if you saw our last course, or if you even know machine learning before, you know that the hypothesis function, for now we use the sigmoid function, but we can use many other functions, but we're gonna focus for now on the sigmoid function. This is the how the sigmoid function is defined. So you can see that it's the h of x is actually w1 multiplied by x1 multiplied by w1, and then we feed it, and then x2 multiplied by w2, and then we feed it, and then x3 multiplied by w3, and then we feed it, plus the bias. Always we're gonna have bias, and then the cell do some calculations. In this case, the calculation is the sigmoid function and give us an output. So this is only one neuron. Let's see a set of neurons. So we have our inputs. Imagine we have three different outputs. Three different cells, as we saw in the biological model for our like real brain neurons. So we have to feed the input to every and each one of the cells, like that. So you can see we fed them all, and then we are going to have biases, and I strengthen the word biases and not bias, because there is a bias for each cell, and then there is weights also considering each input for each cell. So, and then we need an output, but we cannot output just from three cells. We need like one cell to do some final computation and give us the final output. So we feed after these cells do their computations, they output their computations and feed it as an input for a final cell, and then this final cell do the final computation and outputs the final output. So this is more complex than the previous one because now we don't have only one cell. This is actually 3 cells. So 3 cells, and then each cell do its computation, feed it to the final cell, and add the bias, and then output. So in the world of neural networks, this layer called the first layer, or called also the input layer. In some books it's input layer, in some books it's the first layer, but yeah, it's the same thing. Then we have the second layer, or also called the hidden layer. Why it's hidden? Because we don't know the values that it's going to output, because the values are hidden. So we don't know them, so it's called the hidden layer. And then the final layer, it's called the output layer because it gives us the final output. So one thing I want to tell you is we always have like one output layer and one input layer, but the hidden layer, sometimes we have 3, sometimes we have 4, sometimes we have, like in some models, 100 layer. And of course, if you like, the more layers you have, the more computation power you have, and the more complex model you have. So in this example, this simple example, we have just one hidden layer, but it can be 3 with different number of cells. We are going to see it, the computations here more clearly. Let's call our cells A1, A2, A3, and A stands for activation function. What's activation function? Is simply the function that we use to do the computation. So in this case, we have an activation function. Our activation function is a sigmoid function, and that's why we call it activation, because it activates the neuron. Because if for example the value is 0, the neuron is not activated. And then if it's more than 0.5, like we saw in previous examples, 0.5, then that means it's active. So that's why they call it activation function. So for the A1, for the first activation function, for the first cell in our first hidden layer, or you can call it the second layer. First hidden layer is the same as saying the second layer. So how do we do the computations? We take the weight 1, 1. This is not 11. This is called 1, 1. 1. The first one means the weights for the first set of weights, and the second one means from the input number 1. So that one. So this is the arrow that represents this weight multiplied by x1. Okay, then the second one, which is this one, multiplied by x2, and then the third one, which is this one, multiplied by x3, and then we add the bias 1. So this is the bias 1 here, and we do the sigmoid, and then we have this output here. So the output comes from here. And then we do the same for the A2 here, and the same for A3. And as you can imagine, each one has its own weights. So all weights are different here. Each and every weight is different from the other. And then, actually, I think I didn't write it here, but I'm gonna say it to you. Then after doing all these calculations here, we have one output from here, one output from here, and one output from here. All the outputs also are multiplied by their own weights, which I didn't write here. So you can call them W2, 1, because they are the second set of outputs. the second set of weights, because this is here the first set of weights, here the second set of weights. So W21, W22, and W23 multiplied and then fed to this final output layer. Let's suppose it's sigmoid. It's doing as an activation function sigmoid, and then we add the bytes and we have our final output. If you didn't understand, don't worry. We are going to see a very simple and detailed examples in the few next videos, so don't worry about that. So what's the number of weights here? This set of weights. How we calculate the number directly? Simply just by multiplying the number of units. For example, here we have the units are are 3, and here the other units are 3. So multiply the units. Let's call these n, and let's call these m. So multiply n by m, you get 3 by multiplied by 3. That's 9. So if you calculate the weights here, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 weights. If you want to calculate the set of weights here, you just multiply 1, 2, 3 by 1, because this is just one cell. So 3 by 1, 3. That means there is 3 weights, 1, 2, 3, and that's right. So that was our video to define artificial neurons. In the next video, we are going to see exactly how do they work, and how do they interact between each other, and we're going to see like really simple examples, so don't worry about that. If you didn't get it here, just come with me to the next video. Thank you very much, and see you there.